The AAA angle, Similarity Criterion. Welcome, everyone. Today, we are going to dive into a very important concept in geometry, the AAA, or angle, Similarity Criterion. Now, before we jump into the new material, let's quickly recap what we covered in our previous lesson. We learned that for two triangles to be considered similar, they have to satisfy two specific conditions. First, all of their corresponding angles must be exactly equal, and second, their corresponding sides must be in the same ratio, meaning they are proportional. Now, if you were working on a complex geometry problem, trying to check all 6 of those elements, the 3 angles and the 3 sides, every single time would be quite tedious and, frankly, very inefficient. That is where the AAA similarity criterion comes in. Think of this as a mathematical shortcut. It is a powerful tool that simplifies the entire process. As we will see in the next few slides, this criterion allows us to prove that two triangles are similar by checking only their angles. If the angles match, the sides will follow suit. Let's move on to the next slide to see the formal theorem behind this. Understanding Theorem 6.3. Now that we've introduced the concept of the AAA criterion, let's dive into the mathematical heart of this topic, Theorem 6.3. As you saw on the previous slide, checking all 6 elements of a triangle is quite a lot of work. Theorem 6.3 gives us a massive shortcut. It states that if we can prove that the corresponding angles of two triangles are equal, then we don't even need to check the sides. Why? Because if those angles match, the corresponding sides are automatically in the same ratio, or what we call proportion. And once the angles are equal and the sides are proportional, we can officially declare that the two triangles are similar. Let's look at the formal mathematical statement to see how you would write this in an exam. Suppose we are looking at two triangles, triangle ABC and triangle DEF, if we are given 3 specific pieces of information. First, that angle A equals angle D. Second, that angle B equals angle E. And third, that angle C equals angle F. Then, we can mathematically conclude that triangle ABC is similar to triangle DEF. We use this tilde symbol to denote similarity. But here is the most important part for solving problems. Because we have established that these triangles are similar, we can now move from angles to sides. We can state with certainty that the ratio of side AB to side DE is equal to the ratio of side BC to side EF, which is also equal to the ratio of side CA to side FD. In the next slide, I will show you a logical, step-by-step process on how to actually apply this theorem to prove similarity in your geometry problems. Step-by-step process to prove similarity using AAA. Now that we understand the theory behind Theorem 6.3, you might be wondering, how do I actually apply this in a geometry problem? Well, I have a clear, 5-step logical process you can follow every single time to prove similarity using the AAA criterion. First, Step 1, identify the triangles. Before you start calculating anything, clearly define which two triangles you are comparing. For instance, you should explicitly state if you are looking at triangle ABC and triangle DEF. This keeps your work organized. Next, Step 2, match corresponding angles. This is a crucial step. You need to look at both triangles and determine which angle in the first triangle corresponds to which angle in the second triangle. It's all about finding the pairs. Moving on to Step 3, verify equality. Once you've identified your pairs, you must prove they are actually equal. You won't always be given the angles directly. You might need to use given information, or perhaps use properties of parallel lines, like finding alternate interior angles, or even use the angle sum property to find a missing value. Once you have proven that all 3 pairs of angles are equal, you move to Step 4, state the similarity. This is where you use the mathematical symbol for similarity, which looks like a tilde. You would write something like, triangle ABC is similar to triangle DEF, but a quick warning here. Pay close attention to the order of the vertices. You must write them in the correct corresponding order. Otherwise, your statement will be mathematically incorrect. Finally, Step 5, Establish side proportionality. The beauty of the AAA criterion is that once you've proven the angles are equal, the sides follow suit automatically. You can now confidently write the ratio of their corresponding sides as equal fractions. For example, you can state that side AB over side D equals side BC over side EF, which also equals side CA over side FD. Following these steps will lead us perfectly into our next slide, where we'll see this exact process applied to a real-world scenario involving shadows. Real-world example, measuring height via shadows. Now that we have understood the theoretical foundation of Theorem 6.3, let's see how this actually works in a real-world situation. This is where the AAA criterion becomes a truly powerful tool. Imagine you are standing in front of a massive flagpole. You want to know exactly how tall it is, but obviously, you can't climb to the top with a measuring tape. However, you can use a simple trick involving a small stick and the sun's rays to find the answer. Let's look at our scenario. We have a flagpole standing vertically on the ground, casting a shadow. At the exact same moment, we place a small stick, which is 1 meter in height, vertically on the ground, and it also casts its own shadow. Let's break this down step by step using the logic we just learned. First, we need to identify our triangles. Let's call the triangle formed by the flagpole and its shadow triangle A, B, C, and let's call the triangle formed by the stick and its shadow triangle D, E, F. Next, let's look for our first pair of equal angles. Since both the flagpole and the stick are standing vertically, meaning they are perpendicular to the ground, we know that angle B and angle E are both equal to 90 degrees. That's our first match. Now, for our second angle, let's consider the sun's elevation. Because the sun is so far away, its rays hit the Earth at essentially the same angle for both objects. This means the angle at which the sunlight hits the top of the flagpole, which is angle C, is equal to the angle at which it hits the top of the stick, which is angle F. Now, remember what we discussed in the previous slides about the properties of triangles. Since we have already proven that two pairs of angles are equal, the third pair must also be equal. Because the sum of angles in any triangle is always 180 degrees, angle A must be equal to angle D. So we have reached our conclusion. Through the AAA criterion, we have proven that triangle A, B, C is similar to triangle D, E, F. And here is the most exciting part, the application. Because these triangles are similar, their sides are in proportion. This means we can set up a ratio where the height of the flagpole divided by the height of the stick is equal to the shadow of the flagpole divided by the shadow of the stick. If you know the length of the shadows and the height of the stick, you can calculate the height of that flagpole with perfect accuracy. But before we move on, I want to point out a few common pitfalls to watch out for so you don't lose marks on your exams. Common mistakes to avoid. Now that we have seen how powerful the AAA criterion is for solving real-world problems, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to lose marks on exams by making these 3 specific mistakes. First, let's talk about incorrect vertex correspondence. This is perhaps the most frequent error students make. When you write a similarity statement, the order of the letters matters immensely. If you have proven that angle A equals angle D and angle B equals angle E, you must write that triangle ABC is similar to triangle DEF. You cannot simply shuffle the letters. If you were to write triangle ABC is similar to triangle EDF, you are mathematically claiming that angle A is equal to angle E, which we know is not true. Always double-check that your vertices match up in the correct sequence. Second, please be careful not to confuse similarity with congruency. In our previous lessons, we discussed congruency, where triangles are identical in both shape and size. However, the AAA criterion only proves similarity, which means the triangles have the same shape, but one could be much larger than the other. Remember, having identical angles tells us the shape is preserved, but it tells us nothing about the actual scale or size of the triangles. Finally, avoid the mistake of assuming proportionality without proof. It might be tempting to look at a diagram and immediately start setting up ratios of the sides. However, you must follow the logical flow we discussed in the previous slides. First, you must establish that the angles are equal using the AAA criterion. Only after you have officially stated that the triangles are similar can you then conclude that the corresponding sides are in proportion. Never skip the proof of angles to jump straight to the sides. Keep these points in mind as we move toward our final summary of the lesson. Key takeaways. First, let's look at the core rule that we've been discussing throughout this session. Remember, the entire logic of this theorem rests on a single chain of implication. If you can prove that the corresponding angles are equal, this automatically implies that the corresponding sides are in proportion, which, in turn, leads us to the conclusion that the triangles are similar. It is a beautiful, logical progression. Next, a quick reminder on notation. When you are writing your proofs or solving problems, always use the tilde symbol, which we pronounce as is similar to denote similarity. This distinguishes it from the equals sign used for congruence, a distinction we touched upon in our discussion of common mistakes. Finally, let's look at the ultimate result of applying this criterion. Once you have successfully established that triangle ABC is similar to triangle DEF using the AAA method, you have unlocked a powerful mathematical tool. You can now confidently state that the ratio of side AB to side D is equal to the ratio of side BC to side EF, which is also equal to the ratio of side CA to side FD. This relationship is automatically true and is exactly what allows us to solve real-world problems, like the flagpole example we saw earlier. All right, we have reached the end of our lesson on the AAA Similarity Criterion. Let's quickly recap the key takeaways to ensure you have a solid grasp of the concept before we wrap up. Keep practicing these steps, and you'll find that identifying similarity becomes second nature. Great job today.